In section 5.4, we're going to continue our thoughts about the conditional distribution for a two-way contingency table, but we're kind of think of it a different way. We're going to think of it in terms of a conditional probability. And we're also going to apply the general multiplication rule. Now we're going to trim these back to only look at contingency tables for the most part, and then one other topic that we want to talk about, namely sensitivity and specificity. All right, so let's begin with this notation. Conditional probability is notated with capital P for probability and then F/E. That's the probability of F given event E. And this is very much like the given that you were working with in the conditional distribution for a two-way table. You assume a certain thing. You assume you're in this column or you assume you're in this row, and then you find the chances of this other thing happening given that you're in that row and only that row or that column. That leads us to the conditional probability rule, which says that the probability of that F given E is equal to the probability of E and F divided by the probability of E. That's great, but we're not going to use it that much. We're actually going to use the second definition here, which is the number of ways that event E and F can happen divided by the number. So just note, I'll add it in right here. Note N stands for number. And there we go. So that N stands for number of ways, or number. All right, so let's look here. We have the following table shows JC Fall 2011 enrollments by degree type. So we have your associate in arts, your associate in applied science, your associate in general studies, and so on. So we want to find the probability of female given that we're talking about an associate in arts. So there's that given that right there. All right, so the given that means that you're looking at only this column. You're looking at only the associate in arts column. So you want to find the probability of female given AA is the number of ways to have female and AA divided by the number of ways to have AA. So let me write that up. Okay, so I wrote it out in English. It's the probability of female given that they're an AA major. And that's the number of ways to be both female and AA divided by the number of ways to be AA. So I'm using the formula from up above. F for me is female, E for me is AA, associate in arts. All right, so now I'm looking at my table and I'm thinking, well, I need the number of ways to be both female and AA. But female and AA is the 665 cell. And the number of ways to be AA is the 1194. So I'm totaling down this column. So I'm going to take 665 and I'm going to divide it by 1194. And that gets me a number of 0.557. Great. Okay, now we're going to reverse it. Now I want to take the probability of AA major given that they're female. So let me write that up. Okay, so this is the probability of AA major given that they're female. So that means you're going to look at just the female row here. So you're going to say, well, it's still 665 because that's the AA and female, but it's divided by 4001 here because you're looking at the female row only. So notice these answers are not the same thing at all. So one is imagine, or letter A, I should say. Letter A is imagine a room full of AA majors. Then you expect 55.7% of that room to be female. The bottom one is have a room full of all the female students, right? Take all 4,001 female students in a room and you expect 16.6% of them to be AA majors. So let me type that up. There. So letter A was imagine a room filled with all the AA majors that year. Then over half that room would be female. And letter B was imagine all the female students, like everybody in the room is female. Then you'd expect 16.67% of them to be AA majors. Now we're going to expand on this idea just a little bit because this was talking about one student. If you can see right here, we're selecting one student. But suppose I want to select more than one student. Well, that would lead us to the general multiplication rule. Now, if you remember in section 5.3, what you would do is you would multiply, right? But in section 5.3, everything was assumed to be independent. Here, because this is a table and when you pull somebody away, you're not replacing them, they're not really independent, right? So you're going to take the probability of E, but instead of multiplying by the probability of F, which is what you do when they're independent, you multiply by the probability of F given that event E has already occurred. And just make a note down here, if events E and F are independent, then the probability of F given E is equal to the probability of F by definition. So if they were independent, then it would automatically be taken care of, and you'd have your simpler independent multiplication rule that we learned back in section 5.3. So if it's independent, then it's just probability of F. But if it's not independent, or if you don't know if it's independent, then you have to use this more advanced form. In particular, we're going to use it for a contingency table. So let's look right here. Same table as before. We're going to select one fall student at random. I want to find the probability of AA and female using the multiplication rule. Okay, so according to up above, the probability of AA and female is equal to the probability of AA, oops, let me type female, probability of AA times the probability of female given that they're AA, associate in arts. Okay, well, the probability of AA we already know. We figured that out before in a previous section, but let me just remind you, it's equal to 1194, because that's how many AA students there are, associate in arts, divided by the total. So I got to move this somewhere. Here, let me pull this up here. There we go. Divided by the total of 6548. Now I'm going to multiply that by, now I need the probability of female given that they're AA. Okay, well, I did this on the previous page, but I'm just going to remind you, given that they're AA means you're only looking at this column. So that 1194 down there becomes your denominator. So it's going to be 1194 down there, and then female is 665. Now notice what's going to happen here. These 1194s are going to end up canceling, right? They divide away to 1, if you will, and you end up with 665 over 6548, which we actually already knew because we already found it on a previous page in section 5.2, I believe. Or yeah, 5.2. And there we go. So we already found that in section 5.2. I don't recall the page, and of course the page numbers might change from semester to semester. But if you go back there, you can actually find the probability of female and AA because it's this group right here. Female and AA is 665, and you just divide it by the grand total. But now we've proven that that method was correct because you could also use the general multiplication rule to find it.